So what we have seen is a definition of the tangent space of an affine variety at a given point, provided that we have an explicit embedding of this affine variety into affine space. Now, how do we do this when we have an algebraic variety that's not necessarily affine? Well, what we want to do, and what in the end we will be able to do, is to define the tangent space of an algebraic variety simply by covering the algebraic variety with an affine cover and taking the affine open where our point belongs and embedding this into affine space and then computing the tangent space as we did before. But the problem with this is that there are lots of choices involved. There are many ways in which I can find an affine open U containing A. And already, if my variety is affine, there is a problem in the embedding. I am seemingly dependent on this embedding. Maybe I get something different if I choose a different embedding. So is this business independent of all these choices? Luckily, the answer is yes. And the way to achieve this is to realize this tangent space in the affine setting locally as something that is independent of any choice. To do this, we will in the end, so the program is to look at the localization, so the stalk of the coordinate ring at the point A. You might want to briefly review this definition from the lecture on local properties of varieties. But in any case, this ring is a local ring and it has a maximal ideal M, which is the localization of the vanishing ideal of A. So OX, A, this is the localization at the prime, hence maximal, hence prime ideal IA. And so its unique maximal ideal is the localization of the ideal I of A itself. So the functions that vanish at A. And what we will show is that if we take this ideal, so we get a K vector space from it and also from the square of the ideal, and the quotient is a vector space over K, and the dual space of that vector space is isomorphic to the naively constructed tangent space from the previous video. And this is how we know, since all of this data, this M and R, are independent of anything except the variety X and the point A, we will have established that our construction is independent of choices. We will prove this result in two steps. The first step will be without localization, and then we will localize. But just to give you a flavor of this M mod M square business, let's pause and think what this means. So intuitively, modding out M square means that we disregard anything of higher degree than 1. This resembles what we did in the previous video, but in a greater scope, really this is some way of taking limits without taking limits. This is a physicist's way of taking limits. So in calculus, remember, you do derivatives by getting some epsilon somewhere and letting epsilon go to 0. We cannot do such a thing, but we can declare epsilon squared to be 0. And this is our way of letting epsilon go to 0, meaning we choose epsilon so small that its square and higher powers are negligible. This is the philosophical idea behind modding out, or one philosophical idea behind modding out M squared. And I mean, how does this work in practice? So if I take an example, if I take, well, not a local ring, a non-local example, say I take a ring, my ring, say some other R prime to be K of T, and ideal M prime to be the ideal generated by T. Then M prime squared is the ideal generated by T squared. And so then the quotient is just the span of T, the one-dimensional vector space spanned by T. So let us start with the non-local version. So let us now take x, an affine variety explicitly embedded in a to the power n for now, and embedded in such a way that our point A in fact has coordinates 0. So after translation, as we have seen, we can always achieve this. Now, the theorem states as follows, that the map F to F1 induces a natural vector space isomorphism from this quotient space to the dual space of the tangent space. But what does all of this mean? So let's make this precise. What this theorem means is that we have our I of A, the ideal, the vanishing ideal of A. From there, we go to the dual space of the tangent space. So this is the space of linear forms, linear maps from the tangent space, which is a vector space, as we have seen, as we have defined it previously, to K. So this is TAX as defined in the previous lecture. This is well defined because now we have a specific embedding. And so how do I achieve this? Well, so this I of A sits inside OX of X, which is quotient of the polynomial ring by the vanishing ideal of X. So an element here is the class of some polynomial. And I map this to the degree 1 part of the polynomial restricted to Ta of X. The degree 1 part of any polynomial defines a linear form on a to the power n. And so I restrict it to this subspace, and then I get a linear form on Ta of X. So if this F1 is well defined, then the right-hand side is clear. Why do I say if this is well defined? Well, I need to show that this thing doesn't depend on the choice of a representative. So first we need to show that this is well defined. Well, this is because if F bar is equal to G bar, so this means that the difference F minus G belongs to I of X, but this means that F minus G, its linear term as restricted to Ta of X is 0, because this was how we defined the tangent space. So this means that F1 restricted to TAX is equal to G1 restricted to TAX. So this construction doesn't depend on the choice of a representative. This map is linear, so let me call this map phi. Phi is linear because taking the a certain part of the polynomial is linear, and it is surjective. Why is it surjective? Well, because any element here, any linear form on TAX can be extended to a linear form on the ambient space. And any linear form on the ambient space is given in such a way. So indeed, we will be getting any linear form on TAX. So surjective because we can extend anything in this home space to home K of K to the power n, K. And so the difficult part of the proof, or the main work in the proof, is to show that the kernel is, so we want to show that the kernel of this phi is exactly I to the a squared. Because then by the isomorphism theorem for vector spaces, we know that phi will induce an isomorphism once we mod out the kernel. So let's get to business. So first we want to show that the kernel of phi is contained in I of a squared. And remember, phi of the class of f is defined as f1. So assume that f bar is in the kernel. So if f bar is in the kernel of phi, then f1, and I should be precise, this is f1 restricted to the tangent space, is 0. Then the claim is that there exists g that vanishes on all of x, such that g1 is equal to f1. Let's assume for a moment that the claim is true. Then, so if I take f bar, well, since g is an I of x, adding g or subtracting g from f doesn't change the representative, so f bar is the same as f minus g bar. And now both f and g vanish at the point a, which is 0, which is in x. So they have no constant term. So this difference doesn't have a constant term. And because f and g have the same linear term, this difference doesn't have a linear term. So not having a constant term and not having a linear term precisely means that this belongs to IA squared. Because IA is simply those polynomials that don't have a constant term, because a is, so remember here that a is 0. So if this claim is true, we are done with this inclusion. But why is this claim true? Well, assume that, or call the dimension of the tangent space D. Now I want to compare two vector spaces. I want to compare the vector space of all linear parts of polynomials belonging to I of x. And also I want to compare with the space of linear forms, let's say h from kn to k, linear, such that h restricted to tax is 0. And now I'm writing k to the power n for a to the power n with a vector space structure. So if the dimension of the tangent space is D, then linear algebra tells me that this has dimension n minus D. Because this is exactly the linear forms vanishing there. But also the tangent space is exactly the 0 locus of this thing. So this also has dimension n minus D, again from linear algebra, from the 0 locus dimension there. Also, every such thing belongs here, because these G1s vanish at the tangent space. So I have this inclusion. So I have an inclusion of vector subspaces of the polynomial algebra, say, of the same dimension. So therefore I have an inequality, an equality. which means that any linear form that vanishes on Ta of x actually is the linear part of a function in the vanishing ideal of x. And that is why I can always, for my f1, find such a g1. And so this implies that this claim holds. And so we're done with that inclusion. And for the reverse inclusion, well, what I want to do is I want to take two polynomials, f and g, and look at these. And then I claim that fg1 is 0. This is true because fg1 is simply the constant part of f times g1 plus the constant part of g times f1. And f and g, vanishing on a, which is 0, have no constant parts. So this is, maybe I can even write f of a and g of a here to emphasize this. And so this is 0. And why does this help? Well, this means that every product is in the kernel of phi. And this means that the product of the ideal with itself lies inside the kernel of phi, and this completes the proof. So now we have shown that, if we go back one step, that our tangent space, the dual of our tangent space, is this quotient. The next step is to localize this quotient. So to do that, we take an affine variety x, take a point A in x, and let I sub A be the unique maximal ideal of the stalk at A. And recall that this is the localization of I of A. The claim is that we get an isomorphism between the quotient we considered in the previous slide and the quotient in the localized version. So to prove this, we note that this OXA is the localization of OX of x with respect to the prime ideal I of A, or in other words, this is S inverse OX of x, where S is everything except this ideal. To perform all the steps exactly, we really have to introduce the localization of modules. Not wanting to do that, we can still get the idea clear. So first of all, the ideal I of A, localizing it gives us I sub A, and localizing I of A square gives us the localization of, the localization of IA, which is IA squared. These are easy to check. And then localization is such that even in this case where we don't really have rings, but modules over our ring, localization commutes with the quotient. So the localization of IA mod IA squared is exactly IA mod IA squared, combining these with this quotient property. What I want to show is that this S inverse doesn't change anything. And so what does it mean? This means that if I have, so take G sub f in the localization of IA. This means that G of A is 0, but f of A is not 0. then I claim that GF is the same as G lambda divided by lambda, where lambda is the scalar f of A, which is invertible. So this is lambda inverse G. This is something that is already there. So I mean, this f was already invertible. But this is not exactly true. I want this to be true modulo I of A squared. So modulo I of A squared. So what do I mean by this? Well, what would such an equality mean? So if I take f, then f is going to be f of A plus some h, and this h vanishes at A. This is nothing special. I can always do this. So this means that GF is G times FA plus GH. But now, G being in the vanishing ideal of A and H as well, this belongs to the ideal squared. So GF is equal to GFA in I of A modulo I of A squared. And this is exactly what I need for the localization, because remember, this was the definition of localization, how these work. If I divide through by f and this lambda, which is f of A, then I will get my result. So this, a bit hand-wavingly, but still gets the idea clear, that this localization doesn't change my quotient. So this brings us to the definition of the tangent space. A definition that doesn't depend on anything. So take an algebraic variety x and a point A in x, then we define the tangent space of x at A to be the dual space of IA mod IA squared, where IA is the unique maximal ideal of OX, A. So note that here we use that, I mean, this works because of our previous results and the fact that the dual this is TA of x. This is equivalent to saying that IA mod IA squared is the dual of TA of x, because every vector space of finite dimension is isomorphic to its double dual. And so a few remarks about this. So this local ring by construction is independent of both the choice of an affine cover and the embeddings of affine covers. So if you really want to be precise, what we did in the previous two slides, we really only did for affine varieties. But you can always get to this OX of A starting with any open set. So how do you construct OX, A? Well, you start with your variety, you take whichever open set you want that contains A, and you start from there. And because of the definition of this talk, this will not be dependent on what intermediate open sets you took. So this is indeed independent of any choice. And this is also reassuring because, so if I want to concretely compute some tangent space, what should I do? Well, I do not need to worry about this hassle with duals of IA mod IA squared, because really this says that the ancient way, the way that I mentioned in the beginning, by picking an open cover of my choice and performing computations with linear equations, this is okay, and therefore I can reduce to that case and use these computations, knowing that I will get the same result as anyone else who does anything to compute the tangent space.